Okay, is everybody clicked in here? Everybody has their clicker? Make sure you show up there. We good? So I've always believed that the day after the Super Bowl should be a holiday, but unfortunately it's not. So who, the instructor? What time was your class? Yeah. All right, well, that was definitely an entertaining show last night. I won't talk about it because I know some of you are probably upset. So, okay, so we are not doing a quiz today. I hope you're prepared for a quiz. I'm not giving one just because it is the day after Super Bowl and it's, consider it a pass, a free pass. Oh, my, thank you. But I hope you did do the homework, and I'll address any questions. I know that there are some problems in the homework that we hadn't really looked at yet, so if there's something right now that you have a question on, I'd be happy to look at it. But if it's something I'm going to talk about today, then I'll tell you and we'll hold off. 34? And we're talking out of the 5.5? Okay. 34. Yeah, that's a good one. How about I do that at the end? Okay, just remind me because I'll probably forget. Okay? Okay, so 5.5, we had talked about, what was the technique? U substitution, right? And the idea was to look into the integrand, try and identify something and its derivative sitting there. And if you do that, then you can hopefully resolve what the antiderivative is. And I did several examples, and I'm going to continue with some examples right now. And what you're going to see with the ones I'm going to show you now is that the substitution is not as natural as you would think. And I told you, look for something in its derivative, but turns out that sometimes that's not there, but a substitution will still work. All right, so let's take a look at something of that nature. Something like finding the antiderivative of x over the square root of x plus 1 dx. Let me rewrite that. Square root of x plus 1 on the bottom dx. Okay, so if you try and look for something in its derivative here, what are your options? I mean, you could let the x on top be your u, right? But then what's the derivative of x? 1 dx, right? It'll become 1 dx. And my advice to you is when you're using u substitution, never let u be x. Okay, because all you do is rewrite the problem in terms of u. I'll just show you real quick. If I let u be x, then du is 1 dx. Then what would happen is I would rewrite this x on top, right, as u. I would rewrite the x on the bottom underneath the root as u plus 1, right? And then what would dx become? Du. So all you've done is rewritten the problem. You've replaced every x with a u. That's all you've done. So when you're using u substitution, avoid letting u be x, all right? Now, our other option would be, what, to use x plus 1? And what about using the whole thing, the square root of x plus 1? Well, I really don't see the derivative of square root of x plus 1 there. So I'm going to try the x plus 1, and let's just see where this takes me, okay? So what is the derivative of x plus 1? 1 dx. Is it all right if I just write dx? Okay. So now what I'm going to be able to do is I'm going to be able to replace the dx here right? It matches perfectly. I'm going to replace that with u. I will replace the x plus 1 with what? U. And then the question becomes, what do I replace x with? So what I have to notice is that my substitution created an equation, didn't it? The equation has u and x in it. I can take that equation, I can solve it for x. So just isolate x on that equation. Subtract 1 on both sides, right? You get u minus 1 equals x. That means I can replace this x on top, right, with what? U minus 1. Okay, so let's try it, see where we go with it. I'm going to rewrite this integral. I'll have u minus 1 on top. Then I'll have what? Over square root of u, and then dx is du. Now you may argue that I haven't really made the problem any better because I still have a square root in there, right? However, this is what we did in 4.7. This is all power rule stuff. You have two terms on top, right? You have a single term in the denominator. The denominator is a power of u. So in other words, I can rewrite this as u minus 1 over what? U to the half du. And now split this into two separate terms. It's u over u to the half minus 1 over u to the half du. I'm going to put parentheses around that whole thing because I've split a single term into two terms. Let's do a quick poll. Are we good with this or not? Okay. And so now I can rewrite each of those as powers of u, right? I'm not going to take the antiderivative yet. U over u to the half is u to the half. And then minus 1 over u to the half is what? U to the negative half. And at this point, I have powers of u. I'm trying to integrate, trying to find the antiderivative, right? So I just use power rule for each of those. And I hope you've done enough power rule now. What would the antiderivative of u to the half be? 2/3 u to the 3 halves. And then the other one would be what? 2u to the half plus c. So at the point that I actually applied the power rule, my integral sign goes away, my du goes away, the c appears. And I'm almost done except for I need to replace u, right? Get u back to what it is, or what I said it was. So u was x plus 1. So my final answer will be 2/3 in parentheses x plus 1 raised to the 3 halves minus 2 times x plus 1 raised to the 1/2 plus c. And I can box this up. Anybody have a question on this? We're good? This is probably the cleanest, easiest way. Yeah. Yeah, the other technique of integration we're going to talk about today might work with this, but it would probably be more complicated. This is still substitution. The point of this example is that I've told you look for something in its derivative, and here, I mean, I really didn't see the derivative of x plus 1 other than being dx, but I wanted my derivative to be somewhere up here, hopefully, right? But it worked out, and the key was using this little solving for x in the problem. All right, let's see another adaptation of this, or another problem that uses this method. X times x plus 1 to the 100th power. And we would not want to take x plus 1 and multiply it times itself 100 times, right? We could, but We don't have enough time for that. So again, I'm looking for something in its derivative, and I don't want to use x because we already said if you let u be x, you're just going to rewrite the problem. So I need to have something a little bit more than x. X plus 1 seems like a natural candidate for that. I don't want to take x plus 1 to the 100th power because the derivative of that, right, is you have to bring the 100 down, and then it would be x plus 1 to the 99, and we don't have that anywhere there, right? So let me try the x plus 1 again, see where it leads me. The derivative of this would be just dx, 1 dx. So I'll be able to rewrite the dx in the problem. I've got that. I'll be able to rewrite the x plus 1 in the problem. I just need to work on that x on the front. So how am I going to replace the x? Just go over here, solve this for x. I get u minus 1 is x. So very similar to the previous problem, right? Let's see if this new integral becomes something I want to work with. How do I write this? U minus 1, that's x. That would have to be in parentheses. Thank you. Yes, because I'm multiplying it, right? Multiplying it times what? U to the 100th power. And then dx is du. Now, what do I gain by this substitution? What have I gained? What can I do now? Just distribute the u to the 100th power through the parentheses, right? So that's what I'll do. When I distribute that u to the 100th power through, that means multiplying it here and multiplying it here, I get an integral that looks like this. U to the 100th, 101, minus u to the 100, du. Now just power rule. So the antiderivative is going to be 1 over 102 u to the 102 minus 1 over 101 u to the 101 plus my constant. And lastly, we replace u with x plus 1. There we go. U to the 1 where? No, because you can't subtract these. They're not like terms. All right, quick poll, yay or nay on that, please. I do also want to point out that when you look in the back of the book for answers, a lot of times they simplify these quite a bit. So something the book might do here is they may actually pull out a factor, or actually they pull out 101 factors of x plus 1 and leave you with 1 over 102 times x plus 1 minus 1 over 101. So what did they do there? It's the same as if I said, can you factor a u out of both of these? Yes, you could factor out 101 u's, couldn't you? You'd pull them out. That's what I did here. I said, look, I've got 102 of these, I've got 101 of these. I pull out 101 of them. What's left here is the 102, and then I pulled out 101 of them, so I'm left with just one of the x plus 1 factors. I pulled out 101 of these factors, so all that's left is this constant, so that would be here. And then you could actually clean this up, couldn't you? Like you could distribute 1 over 102 here and here, and then combine your fractions together. And the book may have that in the back as an answer, so just be aware of the algebra that may be required. I'm just looking, I'd be happy with this. Okay, let's do something else. Something slightly more challenging. Not too bad, but So can we handle this? So again, I'm looking at this and I'm not seeing something and its derivative right away, right? Are you kind of on the same page with that? So let's take a shot at it. What do you think we should try? Try something, right? You want to try 3x plus 2? Okay, let's see what happens. All right, what's the derivative of that? 3 dx. Do we have 3 dx in our integrand? We don't have a 3, do we? Not by itself. It's underneath the root, but that's my u. So let me isolate the dx here by multiplying both sides by 1/3. So I will be able to replace dx here, right, with 1/3 du. I will be able to replace 3x plus 2 with u, right? But what about the x plus 1? I mean, that's the same thing I did earlier, right? I'm going to have to figure out what x is, right? So solve that for x. So first subtract 2 on both sides. And then what? Divide by 3 or multiply both sides by 1/3. I just multiplied both of these by 1/3. So I got 1/3 u minus 2/3 equals x. Okay, yes or no? Now we have to make some choices here because I know I can replace this x with x plus 1, right? I mean, sorry, this x with 1/3 u minus 2/3. But I have a plus 1 next to it, right? So I have to make sure that when I plug this thing in, I tack that 1 on next to it. Just make sure I don't forget that. So here I go. I'm rewriting the integral. It will be 1/3, yes. I have 1/3 u minus 2/3. That's what x was. Then plus 1. Remember that 1 is coming from there. And then square root of u. And then 1/3 du. That's my dx. Okay, yes or no? Hate to have to make you keep clicking, but I want to make sure no one's not losing anyone here. All right, let's clean this up algebraically. When I put these two together inside the parentheses, negative 2/3 plus 1 is 1/3, right? So I'll have integral, I'll have 1/3 u plus 1/3. On the outside, I've got, how about u to the 1/2 instead of square root of u? And how about that 1/3 that's back there on the du? Why don't we pull that completely out of the integral? So that 1/3, I'm just going to pull it all the way out, rewrite this as a power of u, clean this up, and then now I should be able to distribute that u to the 1/2 through, right? That parentheses. So I have my 1/3 on the outside, integral. What are the two terms that are here then? You're multiplying u times u to the 1/2. U to 3/2, and I have the 1/3 in front of it, right? 1/3 u to 3/2 plus 1/3. No, the third that I took out was the one that came back here from dx. I could take out another third. In fact, I thought about doing it, but I was like, nah, maybe it's too much right now, so decided to leave it in there. That's 1/3 u to the 1/2 du. Now I'll pull the 1/3. So that was just this times this. U to the 1/2 times 1/3 is this. Now you do not have to take a 1/3 out here, okay? You could just do antiderivative, but I'm going to take another 1/3 out, right? These both have 1/3. Factor it out, then outside the integral, bring it outside, and what would I have? I'm multiplying them, right? 1/3 times 1/3, which would give me 1/9. And now that leaves me just u to the 3 halves. Yeah, I did. Just trying to confuse you. All right, and then at this point, you take the antiderivative there, right? So the 1/9 is here, right? Let's just not forget that that 1/9 is still in our antiderivative, right? And then we have 2 terms for our antiderivative. I'm going to just put a set of parentheses here and go ahead and give you the antiderivatives. What's the antiderivative of u to the 3 halves? 2/5, u to the 5 halves, and then plus 2/3, u to the 3 halves, plus c, right? Now where do I put the plus c? In here with the parentheses, outside, does it matter? It actually does not matter, okay? Because you don't know what the constant is, right? So I'm just going to say that's it, and then plus a constant. Because whether or not it's a constant or 1/9 a constant, I still don't know what it is, right? So just leave it on the end. And now I would distribute the 1/9 through. So we should have 2/45. Replace u with what it was. So 3x, what was it? Plus 2 to the 5 halves. And then plus 2/27, 3x plus 2 to the 3 halves, plus your constant of integration. See, if we did a quiz, we'd probably just be finishing it up, and I've already done, what, 3 examples for you? So to me, it's more valuable to see problems than to be quizzing you all the time. But you'll have one next time. All right. No problem. Okay. Quick poll here. Let's see if you're okay with that or not. All right, there's one more in basic substitution that I want to talk about. It's nothing fancy. It's just, well, let me just do it and see what you think. That's what we need to determine, okay? So according to what I've put up here, you want the antiderivative of e to the negative RT over v, all right? What is the variable? T. How do you know that? It says dt, right? So you know that the t is being treated as a variable. Now the question becomes, what's r and what's v? In a Calculus 2 class, r and v are constants, all right? Cal 3, r and v could be variables. And so you have to ask yourself, how do you integrate something that has 2 variables in it instead of 1? But that's beyond the scope of this class. So we will assume that in any problem that's given to us, unless it's another class other than this one, you'll just assume that the dt designates your variable and that everything else is a constant. So this may as well be this integral right here. I could plug in anything I want for r. This may as well be negative 2 e to the negative 2t over 5. I mean, it may as well, right? The r is some number I don't know. The v is some number I don't know. So what I'm going to do is I'm going to realize that if I let u be the entire thing up here, right? If u is this, that would be the same as me letting u be this up here, right? What would the derivative of this be? Negative 2/5, right? dt, wouldn't it? Because it's just a constant in front of the variable. So if I let my u be this entire expression up here, negative RT over V, then the derivative of this should be what? negative r over v dt. And I'm trying to rewrite this. I know that this e to this is going to become what? E to u, but dt needs to be replaced, which means I need to solve this for dt. I don't have a negative r over v sitting anywhere here, do I? No. So I have to actually multiply to get this out of here by the reciprocal. So I can write negative v over r du equals dt. So all I did there was multiply both sides of this by the reciprocal, and that gives me a nice equation that has dt isolated. So I can replace that dt with this, and I can replace the entire exponent with u. All right, let's take a vote here. Yay or nay on this? Anybody in here have to take differential equations or have to take engineering analysis? Okay, in engineering analysis, you deal with differential equations, and within differential equations, integrals like this appear a lot, and so this should become very, trivial to you. As soon as you see that up there, you should realize this substitution is not going to be that bad. Like once you do the substitution, the integral is going to be nice. You just can't freak out when you see all those letters, all right? E to the 2x. It would actually make it more complicated if you took e to the 2x and you replaced it as e to the x times e to the x, because that's what it would really mean, to square it. That would be a little more complicated than just using the 2x as your u. And it's just because the 2x is linear. So the derivative of it is just a constant. Yeah, we did something where we rewrote e to 2x as e to something squared to make it match that arctan formula, because we wanted something squared, right, in our formula. Here we don't necessarily want it because we're not going to go for that formula. So again, it's one of those things you just got to, after you've seen enough of them, you're like, I don't want to go that route. Okay, how am I going to rewrite the integral? What does this become? Integral e to the u. Okay, that part's pretty clean, I think. And then I'm replacing times negative v over r du. Okay, now what can I do? Before I take the antiderivative, what can I do to lessen the confusion of what I'm looking at here? Pull the constant out. The constant is negative v over r. And then now you're looking at the antiderivative of e to the u du. And that's one of your antiderivatives that you all just need to know, right? That's on your table of integrals. The antiderivative of e to the u is itself, plus a constant. So I'm going to get negative v over r e to the u, right, plus a constant. It's e to the u. Wait, say again? Yes, is only if it's linear. Because if you have like e to the x squared, that wouldn't work. Okay. You could, in this case, do that. But I'm just saying in general you couldn't, yeah. Okay, so I'm replacing u now with what u was, which was what, negative rt over capital V. My V looks like an R. Plus my constant, that's it. Okay. Yay or nay on that, please? So far, everything I've done, I'm getting like 100%, everyone's following it. So why is this class so hard? It's easy to watch someone do it, right? I mean, you have to, when you're sitting down by yourself, that's when the challenge comes. So I've already said it, you got to practice, you got to keep trying, keep trying, keep trying. All right, so now the homework question. Someone asked about this integral, what was it, x cubed over square root of x squared plus 1. Ooh. Dx. All right, so when I'm looking at this, I'm thinking, okay, look, if u is x cubed, what's the derivative of x cubed? 3x squared. I have an x squared here, right? However, I said in my notes here something very careful, to be very careful with. The derivative should appear in the numerator. Whatever you choose for u, that derivative cannot be in the denominator, and it cannot be trapped in the root. It can't be mixed in with other stuff, because remember that du's always got to be able to be pulled off to the side as a factor, multiplied. So when I'm sitting here looking at this, even though the derivative of x cubed is x squared, and it's here, it's down in the denominator, it's under root, I'm going to totally avoid that. All right? That's the first thing. Now, the other thing I'm thinking when I look at this is, didn't I have a formula? Don't I have a formula for this situation? Arctan is when you have no root there, right? What if you do have the root there? Arc sine? Sine's negative. So which one is it? So pull out your formula sheet. I want you to find it on there, because it doesn't. Okay. Right here. Right? So look at your integration. Oh, you don't have the other ones. Okay. Hyperbolic sine, right? Sine hyperbolic. There's more on the inverse. So it's the antiderivative of that is the inverse hyperbolic sine function, right? Okay. But I don't have this, do I? I have an x cubed on top. I can't just do this. I cannot say that's x cubed. This is a big, big no-no. Okay, you cannot just make this two separate integrals like this. Sorry, I should put a dx here times. You cannot do that, all right? All right, that's a no-go, because that would mean that you're allowed to. That would basically be saying that when you take the derivative of a product, it's just a derivative of each one, but we said the product rule doesn't work that way. We said antiderivative doesn't work the same that way backwards. You would be implying here that you can find an antiderivative of a product by just taking the antiderivative of each of the factors. So you cannot do this. But I just wanted to point out that as I'm looking at this, I am thinking those two things first. The derivative of x cubed is x squared, 3x squared, but it's trapped. I'm thinking I do have a formula for this somewhere, except that the x cube's up there. I could do that, but that's what I'm saying. Once you have the two separated, you can't do each one individually. You can break up integrals with addition and subtraction. You can split them apart. But if it's multiplication between them, you cannot. Substitution? What? Want to try something? This is a good example where you just have to try something. So how about u is equal to x squared plus 1? Now, I understand. I do not see that derivative there, okay? I don't see it. Well, I'm lying, but it's not obvious. Okay, do you agree with this? Okay. Now, the problem we have is that if I rewrite this integral, let me write it in a way that looks a little bit nicer. This is the same integral, right? I don't know if this is what you were suggesting, but I can't do each one separately. Okay. Okay, so I'm going to rewrite it this way. I really would love for this to be x. Well, I'd love for this right here to be x cubed dx, right? Okay, you can't cube both sides and then have a du cubed. You can't do any of that, all right? So watch this extremely clever thing, all right? Well, I mean, you may not think it's that clever, but what do I really wish was there? Maybe I just write it down. How about this? Do you agree with this? Do you agree that x cubed is x squared times x? Yes? Okay, if I do it that way, then can I get this x dx out of this thing up here? Yes? By dividing both sides up here by 2, right? So I'm going to take 1/2 du. That'll give me my x dx. So I will be able to replace that x dx with what? 1/2 du, yeah? Okay, and I know that I'll be able to replace the x squared plus 1 with what? No, the direct substitution. That's my u, right? That's going to become a u, square root of u on the bottom there. The question is, what about this x squared? I can do what? Go back up here and solve for x squared, right? That equation up here has x squared in it. So isolate x squared, wouldn't you get u minus 1 is x squared? And that's exactly what it is that I'm trying to replace in here. This x squared can be replaced with whatever that x squared is. That's kind of clever, right? I mean, that's not as obvious as just your first basic substitution problem. If it was x to the 4th there, this would not work, okay? If it was x to the 4th, it wouldn't work. Because when you peeled it apart here, you would have x cubed times x, and then what are you going to replace x cubed with? Well, you don't have an x cubed up here, so you'd be kind of stuck. Okay, let's take a quick poll. How you feeling about this? Yay or nay? All right, good. All right, let's rewrite the integral. This integral is now going to become what? 1 over root u. I'm going to write u to the 1/2 times. I'm going to go in the order that I have them here. X squared, which would be my u minus 1. I need that in parentheses. Times now my x dx, which is the 1/2 du. I'm going to go ahead and pull that 1/2 all the way out and just tack on my du at the end there. And that's really just 1/2 u minus 1 over u to the 1/2 du. And what can I do with that? Split it into 2 separate problems, right? Because you have the u over u to the 1/2, you have the negative 1 over u to the 1/2. You rewrite those as powers, you do the antiderivative. I'm done. Dot, 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 you do the rest. Is that enough? Is that good? Yes? Okay. All right. We are going to move on. What homework assignment did I give you all last time? 1 through 36 all? Yep. So see how that goes. All right, for 5-5, 1 through 36 all. And we're going to move on. So now we move to the next technique of integration. Were these notes online? I think they were. The next technique of integration is known as integration by parts, or IBP. And it's very interesting where this thing comes from, all right? If you recall from Calculus 1, that if we were given 2 functions, f and g, which in this case, instead of calling them f and g, I'm going to call them u and v, then if you were asked to find the derivative of u times v, you would have to employ the product rule, which would tell you that it's vu prime plus uv prime, right? And there's different ways different books have these orders, but I want you to all agree that this would be okay. right? That is a form of the product rule. So now what we're going to do is we're going to undo the derivative here by integrating both sides. So if I take the antiderivative of u times v, what should I get? So what's the antiderivative of the derivative of something? Don't they undo each other? Yes? So I'll do it in a second, but I would take the antiderivative here, the antiderivative here, and the antiderivative here. Why am I allowed to do these two as two separate ones? Because they're added, right? So now what we're going to do is simplify the left side. The antiderivative of u times v, the antiderivative of the derivative of u times v, the derivative and antiderivative cancel, so we just get u times v. The antiderivative here we cannot figure out. The antiderivative here we cannot figure out. So we just leave it. Now what we're going to do is we're just going to rearrange things, all right? So I'm going to take this right here. I'm going to move it to the left side of the, no, I'll leave it on this side. I'm going to move this one right here to the other side. So I subtract it. And then what you get is this equation right here. That's just rearranging what was there. I'd like to know if you're following at all with what I'm saying here, if you're just like, okay. Okay, so that's less than, yeah, that's definitely less than 80%. So what are the questions? I need you to actually tell me what it is that you have an issue with. Right here? Okay, so I'm subtracting the entire integral right here on both sides. If I do that, it goes away on the right, and it appears over here as uv minus this integral, right? So I've just rewritten that, except I'm putting the left side on the right side. So there's uv, there's minus that integral right there, and then this integral is positive, isn't it? So it's right here. It's like me writing, if I write an equation like this, x plus 1 equals 3, I can write 3 equals x plus 1. It doesn't matter which way I do the equation, right? So I just switched it. That any better? Clarification? No? What else then? No? That's all I did, rearrange it. All right. Yeah, repoll. Yes or no? And if you're just saying yes because you just want to move on, you don't even know what you're supposed to ask me, you're just confused overall, then just hang tight. This is our formula, all right? This is our formula that we're going to use for integration by parts. And I'm going to explain it, all right? Let me just give you a little thing that you can remember it by. You can remember the phrase ultraviolet minus voodoo. And what it is here's ultraviolet minus, and then you have to remember the integrals here. Integral voodoo. So ultraviolet minus integral voodoo is what you can remember. No one ever writes minus integral voodoo. That's the way it was shown to me many years ago. All right, so that's the formula. Let's talk about what this formula does, because that's kind of the key to it. The integration by parts is what we call a transferring of the derivative. All right, what I want you to notice in here is that what we're going to do is we're going to start with an integral that looks like the left side. Okay? So we're going to start, our original problem is going to be some integral, and what we're going to be looking for in that integral is a function, u. Okay? And next to it, being multiplied, is not the derivative of u, but the derivative of something. Okay? The derivative of something. They don't have to be connected to each other. Remember, with basic substitution, you tried to find a u, and then you tried to see its derivative sitting there, right? This one, you're looking for a u, and then you're looking for the derivative of anything that you actually know. So like, for example, if x was sitting there, you know that, like, let's say this right here was x. You would like that because do you know where that comes from? X is the derivative of what? 1/2 x squared, right? So find something and its derivative, and then in the formula, what happens over here? You get a new integral, so you're like, well, why does this even help? What's the difference in the new integral? Instead of having the u, what do you have over here? Its derivative is on the new integral. And then instead of having the derivative of the v here, you have its antiderivative. So notice you've transferred the derivative from the v onto the u, right? So integration parts is a formula that allows us to transfer the derivative. And it's very useful in integration technique when you're trying to integrate. So this is summarizing it. If we're presented with an integral, we try to identify two parts within the integral. U, which is some function that we know the derivative of. Because remember, in the formula, whatever's here, over here, the derivative is going to appear, right? So whatever we choose for our u, we better know what the derivative of it is. And then we're going to choose a v prime, the other part, that we better know the what? Antiderivative of, right? If we can do that, we're going to create this new integral, and hopefully it'll be easier to integrate. And here are the examples we're going to do. And each example, there's a certain kind of strategy that I put in parentheses to the right. Right? The first one's a very basic integration by parts. The second one's not so obvious. The third one, you're not going to like. The fourth one is really what it says there. I mean, we're going to kind of do something kind of weird that you're not going to expect. And then, you know, the rest. So let's start with the first one. So I've got x, I've got sine 10x dx. Now we've talked already about how what makes this course get more and more challenging is not knowing the technique that you're going to need to use when you get to the test, right? So now we start running through our techniques. First, is this power rule? Do you see x's to powers here? Well, not the sign's thrown everything off, right? So we kind of throw that out. How about a basic substitution? Do you see something in its derivative? If you were going to try a substitution, what would you go for here? 10x, right? And it won't work, all right? Because if you do it, I'm doing it super fast here, don't write this down. Your new integral would become okay, so what happened here was I let u be 10x. The derivative of that is just 10 dx. I solve for dx, so I divide both sides by 10. That's going to give me a 1/10 that's going to come out. I need to replace this x with something. So what do? I solve this for x. I get 1/10 u. That's here. I replace the 10x in here with u. I get sine u. What's the problem with this integral? Basically the same as this one, right? I mean, I still have a u on the outside. The variable is still on the outside. I still have the variable inside the sign. So I haven't really done anything to make it better. Okay? So that's going to fail. But you actually might have to do that first and see that it's not going to work before you start thinking integration by parts. So now for integration by parts, I want to remember what was it? U v prime must equal ultraviolet minus integral v u prime. Now, I'll put underneath here another way of, I don't know why I didn't put this in my notes. This is another way of remembering it. See, v prime is the same as dv, right? The derivative with respect to, or the derivative of v. And then over here, u prime is du. So this is better if you're trying to do ultraviolet minus voodoo. It makes a little more sense, right? And this is really what I think I'll use for the rest of the class. I won't use the prime notation, right? I'm just using a different notation right there. So to start the problem out, I need to be looking at an integral that looks like this, u dv, right? So let's talk about this. I have a product here, right? X times this. I would like to see if possibly one of these is something that I could let u be, and the other one let dv be, or the derivative of v. So which one should I use? X is u, and that would mean your dv has to be everything else that's here. Yes? That's one option I could use here. Let's just draw this under here. I could let that be u, which would mean everything else here has to be my dv. The other way you could do it, okay, or you could let this up here be your dv, and then you let the sign part be your u. So let's talk about which one's better. Or let's take a poll and make sure everyone understands what the hell I'm talking about right now. Are you comfortable with where I am right now, trying to make this choice of which is going to work? One is easier than the other. Let's see which one. So what did I say? Integration by parts is the whole idea behind it is a transferring of the derivative, right? A transferring of the derivative. Whatever you choose u to be, in the new integral, you're going to be looking at what? It's derivative, right? And then whatever your dv is, in the new integral, it's the antiderivative. So you've transferred derivative. Which one would you like to transfer the derivative on? So let's start with the first one. If that's your u, what's the derivative of it going to be over in the new integral? 1 is nice, isn't it? And then my dv is sine 10x. The question is, can you find the antiderivative of sine of 10x? I hope so. You're going to have a basic substitution, but you could, or if you've gotten to the point where you can just do it mentally, but everyone here should be able to take the antiderivative of sine of 10x. So that looks like a pretty good candidate. Let's look at it the other way. If we let our u be the sine 10x, can you tell me what the derivative of it is? Yes, cosine 10x times 10. That's fine, right? Well, I can handle that in the new integral. But what about this? If my x is dv, then I'm going to need the antiderivative of it in the new integral, which would be what? 1/2 x squared. So now you've got a 1/2 x squared and a cosine 10x in the new integral, don't you? And isn't that more complicated than what we have here? The new integral would become more complicated. You wouldn't get the answer the other way. If you went with the bottom one, every time you did it, it would just get more complicated. And so you'd never actually get to it. Yeah. So your choice of u and dv here is very important. But you have to understand why it's that way. Okay, just a poll. Do you understand why I want to choose u to be x and sine 10x to be my dv? All right, I think that's enough to move on. So let's do this. I'm going to start the whole problem over. That was just to get you thinking about it. Here's my x. Here's my sine 10x dx. Now, I like to do it this way. I've seen different instructors do it different ways. I like to draw a table to do my integration by parts. And you can just do it over here on the side if you want. And your table is always going to have 4 things in it, all right? It's going to have whatever you choose your u to be. And below it, I like to write du. And then it's going to have whatever you choose your dv to be and your v. So you have uv on top and you have du and dv on the bottom. For this integral, okay, for this integral right here, I have chosen my u and my dv, right? Those are the 2 things that are going to come from this integral. The u that we've chosen is what? U is x. And the dv I've chosen is sine 10x, and do not forget this part, dx, because this is a derivative, right? So you have to have your little dx on the outside. So that dx is always going to follow the dv when you rewrite these. Now on this one, I'm going to move down, straight down. From here to here is differentiation, isn't it? From u down to du, I take the derivative. So what's the derivative of x? 1 dx. So I'm going to write dx. Don't ever just write just 1, okay? Write 1 dx. And then on the other one, what am I going to need to do? To go up, back to recover v, I need the antiderivative. Okay, so you'll have negative 1/10 cosine 10x. Now you do not need to put plus c here. We'll do a plus c at the very end of the problem. We don't need to carry a c throughout this part. Now, I will state that this going from here to here might, for you, be something that you do on the side. You know, that you just, move away from your work, get a piece of paper out, and do your integral. You know what I'm saying? Like, you might not be at the point where you can do this mentally yet, which means you probably haven't done enough yet. Problems, because there's a pattern to these after a while when you're doing antiderivatives of sines, when you've got like linear things in here. So you could do that on the side. Hopefully you just do something like, I need to know what the antiderivative of sine of 10x is. So I'm going to make a little substitution over here of u is equal to 10x, and then du is 10 dx, and then I try and rewrite the integral, right? That's substitution. That's the technique we used before this class. When you do that, you get this. Okay. Yes or no, real quick? We're not done, right? All I've done is created the table. Now I'm going to actually use the formula. Okay, the formula says that this integral here should turn into ultraviolet. No integral sign, right? Ultraviolet, which is u times v, which means I'm going to take this u right here, which is x, and I'm going to multiply times this v right here, which is negative 1/10 cosine 10x. And that will give me negative 1/10 x cosine 10x. So this right here is u times v. What's the rest of the formula say? Minus integral v du. So I'm going to write down here minus integral v, which is this, times du, which is just dx. So I'm going to have a negative 1/10 cosine 10x, then what? dx. Questions? Yes or no? Are we good? This is our first integration by parts one, so I'm going to make sure I don't want to leave anyone behind on this. Well, I don't want to leave 20% of you behind. Come on, vote. I know there's like at least 20 of you in here. Okay. All right, now I'm going to just clean it up. So what I mean is I'm going to take, I don't like that negative, and then there's a negative inside and the 1/10. I'm just going to pull all that out, make it a plus. So I'm not doing any antiderivatives yet. Out of everything? Yes? I would wait till after this antiderivative, because you're going to have another 1/10 that's going to pop out. So I would just hold off on it. That's what I would do. You could if you want. So I'm pulling a positive 1/10 here. The double negative makes it plus, and I've got cosine 10x dx. And now, check this out. I should be able to handle this antiderivative now, because there's no x in front of it anymore. That's the beauty of the integration by parts, is with that transferring of the derivative, that x that used to be out there that was a problem went away. The sine thing became just a cosine thing, which I can still find the antiderivative of. So antiderivative of cosine of 10x is 1/10 sine 10x. So we'll have negative 1/10 x cosine 10x plus 1/10. Now here's the antiderivative, 1/10 sine 10x. Then plus c. So this part here, this antiderivative, right, all of this just gave us this part right here. Right, the integral sign goes away. I guess you could say the plus c is part of that also. Right, this integral here became all this. I don't like all that highlighting. And really the last thing to do is just maybe put these two together and make it 1/100th. Or if you wanted to, you could factor out that 1/10. Either way, we're there. That's it. This is the antiderivative. You know, I'm gonna go ahead and put those 1/10ths together. I don't feel like writing another line. I'm out of space on this page. So that's 1/100th, right? Instead of 1/10. It's kind of crazy, but I mean, that's the antiderivative of something that looked pretty, you know, this wasn't too bad, right? X times sine 10x. What's the antiderivative? Oh, negative 1/10 x cosine 10x plus 1/100th sine 10x. The only way to check this answer would be to take its derivative, right? But what we've actually done is we've undone the chain rule here. So we won't check it. Okay, we good on this problem or not? Let's do some more. The next one was a not so obvious integration by parts. Not so obvious. Just run the ball, man. Wow. I know what I've heard. What have you heard? Yeah. That worked out real good. Yeah. 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 All right. Well, see, again, you know that this is integration by parts because that's what we're doing, right? But let's still run through the ideas here. Power rule, throw that completely out the window, right? Also, is this just a common formula? Well, you know what the derivative of an arc sine is, right? The derivative, but not the antiderivative. You can look off your cheat sheets. There's no formula that I give you for finding the antiderivative of the arc sine. So we're stuck with that. Basic substitution. The only thing you could plug in here would be pi x, right, for u. The derivative of pi x is pi. It's still not going to help you. You could pick the whole thing to be u, right? But do you have the derivative of that whole thing anywhere? No. So you got to try something. And if I'm going to use integration by parts, I'm going to have to complete this table, which means I have to choose something for u and something for dv, right? Those are the two things I have to figure out if I'm going to proceed with this formula or with this approach. Yeah, we know that dv can't be arc sine, right? Do you all agree with that? I cannot let dv be arc sine because if I knew what the antiderivative of arc sine was, I would already have been able to give you the answer, right? But there's really nothing else I can choose for u, right? I mean, like I'm limited here. So if I'm going to let u be the arc sine, the question would be, in the new integral, I would need to know the derivative of that, right? Do you know the derivative of arc sine? Yes. What do you choose for dv? dx. The dx by itself is actually just like a 1. So it does not maybe appear obvious right now that this is going to work, but let's try it. I'm going to let my u be the arc sine of pi x. I'm going to let my dv be dx. And let me start with the dv first. Let me go up to v because that's the easiest part of this. The antiderivative of 1 dx is what? X. Just x, right? So in other words, the derivative of x is just dx or 1 dx. I will need the derivative of this here. So we go to our formulas. What's the derivative of arc sine? What's the derivative of arc sine of u? 1 over 1 minus x squared? Negative 1? Is it negative? It's just positive. Why am I putting x there? It's u squared, sorry. And then times the derivative of u. We'd have to do chain rule in there, right? That's a formula we have, right? So for us, u is pi x. So the derivative of u would be, derivative of arc sine of pi x would be 1 over the square root. I'm out of room. I'm gonna rewrite this, give myself a little more room. Is 1 over the square root of 1 minus pi x squared, right? So how about I write that pi squared x squared? I could leave it as pi x in parentheses squared, but I'm just square the pi and square the x. And then times the derivative of pi x, which is pi, and then I always tack on to the end of this, dx. Okay, let's take a poll. How many of you are with me still? All right. Now, I did this just because, well, that was the only option we had, right? But let's take a look, because you always want to be trying to look a little bit ahead of where you're going. Is this going to be useful to me at all? So I need to look at what's my new integral going to have in it? Voodoo, right? Voodoo. So if I take v and multiply it times this ugly thing, right? Am I going to be able to integrate that? So I'm going to write it on the board because I really want it to be almost mental. You're seeing it in your mind here. It's going to be a new integral, right? It's going to have what on top? The x and the pi, right? So it's going to be pi x. Can I pull that pi out? And then what will be on the bottom? 1 minus pi squared x squared dx. That's the new integral that you're seeing in your mind. This is voodoo, isn't it? Integral voodoo, that's it? And so when you look at that and you ask yourself, can I integrate that? Yes or no? Well, guess what? 5.5, basic substitution. Do you see something in its derivative? What about 1 minus pi squared x squared? What's the derivative of 1 minus pi squared x squared? Negative 2. The pi squared is a constant, right, in front of x squared? And there's a negative there? Derivative of 1 is 0. The derivative of negative pi squared x squared is negative 2 pi squared x, right? dx. You're off by a constant because you have the x up top, don't you? You have u du there. So you'll be able to do basic substitution on this. So this is going to work. But let's just go through it, all right? So I don't know if I can try and get you to see what I'm thinking, or if this is even helpful to you. If I'm going through this and I'm looking at this, forget I set up integration by parts. Here's what I'm thinking, all right? I think I'm going to do that with integration by parts. Therefore, I'm going to let that be my u. The arc sine is going to be my u. The derivative of that's going to have like something, and then it's going to have like square root. It's going to have like x squared down there, right? And then my v in the new integral is going to be x. So I have an x on top, and I've got an x squared in the bottom, and that's x squared and x you know, x squared is my u, x is my du. In some way, that might work. I don't know if that makes any sense of what I'm trying to get you to see. But if not, you just have to draw your table and hope for the best. The good news, we only had really one option here for u. There's only one thing we could use. All right, here we go. All right, this becomes equal to ultraviolet, that's easy, x arc sine pi x. Okay, here we go. Minus integral voodoo. And y'all were okay with me pulling the pi out? Yes? And then leaving that x up there. Can I pull the x out? No. So here's where I am. Now I'm going to do my scratch work over here on the side. I want to know what the antiderivative of x over square root of 1 minus pi squared x squared dx is. Notice that I'm just looking at this integral. I'm not even looking at the negative pi. I'm just going to figure out what the antiderivative of this is. Once I figure it out, I'll plug it in. So I said that we're going to attack this with what? U sub. So here we go. I let my u be what? 1 minus pi squared x squared. The derivative of that is, yeah, so the 1's gone. The negative pi squared is a constant. Ignore it for right now. The derivative of x squared is 2x. Now put the constant back in front. You've got negative 2 pi squared x dx. Therefore, let me get to that. Yes. I know I'm going to be able to replace everything underneath the root with my u, right? That's going to be replaced with u. I want to make sure everyone is clear here that you understand we are going to try and replace x dx. Right? I'm trying to replace the x dx, which is still there. I have x dx right here, but I need to isolate it. So I'm isolating x dx, which would give me 1 over 2 pi squared, I need to make it negative, right? Du would be equal to x dx. Can y'all read this? I know it's kind of getting small over there. Are we okay? We're on the right? All right, let's rewrite this integral. We're still working in the scratch work here. What does this integral right here become? The x dx is all this, is this right here? So can I pull this constant out, negative 1 over 2 pi squared out? Then we have 1 over the square root of u du. This is really u to what power? Negative 1/2? What's the antiderivative of u to the negative 1/2? 2 u to the 1/2. 2 u to the 1/2. So when I take the antiderivative here, I'll get negative 1 over 2 pi squared times 2 u to the 1/2. I'll do square root of u. Plus a constant, right? But I'm going to add my constant in later. The 2's cancel, and which leaves me with a final result here. I think I'm out of space. That's it. This is going to be equal to negative 1 over pi squared square root of u, but what was the u? Now be careful, we're in our scratch work, right? The u that we chose is not the u we had up here, right? The u we chose here was what? 1 minus pi squared x squared. Okay. That expression in the bottom right-hand corner replaces the integral in our integration by parts formula, right? That is the antiderivative. So let me come back up here. I'll take a vote right now. See if y'all are still alive there. To the 1/2? Oh yeah, on top of this? On top of the, yes, but I always leave my constants because I'm about to attach it to another constant up here. See, I'm going to come back up here and remember that's all this, right? This whole integral is being replaced with this answer, but what was in front of that integral? A negative pi, right? A minus pi, and one of those pi's is going to cancel with one of these pi's. So, and the negatives are going to make it positive. So I just kind of leave my constant out there and just let things kind of clean up first. So here we go. This is equal to x arc sine of pi x minus pi times -1 over pi squared times the square root of 1 minus pi squared x squared plus c. Now there's my c. And also be careful here because this is negative pi times the integral, right? You don't want to put negative pi minus this because you have to multiply this together. So those two negatives become a plus. And then one of the pi's cancels. X arc sine pi x. Then what? Plus 1 over pi square root 1 minus pi squared x squared plus a constant. Okay, let's take a vote. All right. So I wanted to pull up Wolfram Alpha. How did I know the first thing on the internet would be something to do with that? Okay, so how many of you have seen this website? I think okay. So if I want to integrate, what was it? Arc sine of, if you just do pi times x, let's just see what happens here. There it is. Right, that's what we got? X arc sine, or sorry, yeah. X arc sine pi x plus 1 over pi square root of 1 minus pi squared x squared plus a constant. Can you mind shutting that door? Just kicking the little thing out of there? Thank you. And this really, you know, showing you this, you know, you have this constant debate that's happening in education, right? You know, if this technology is out here, then, you know, why is it that we need all this, right? So I've always been somewhere in between because I enjoy using technology. When I was a student of calculus, we didn't have this, and you know, so I'm not saying like no because I had to suffer, you have to suffer. But this is the way it is, and the thing is, there's a danger. Okay, like I see the advantage of let's let the computer do this, and let's actually just spend our time doing applications. And when we get the integral set up, let the computer do the integration for us. The danger in that is what is known in computer science is the black box theory. So what happens is you start to educate people, right? And you get these engineers and things like that, and they all turn to the computer to solve the problems. And you have fewer and fewer people that actually understand the code that was made to actually the algorithm that was created so the computer could actually do this, right? So it's the black box. The engineer puts in the problem and it spits out a solution. The engineer trusts that solution, but really has no idea how the computer got to that solution. And that's pretty dangerous. Even back when Wolfram Alpha wasn't there, when I was in, I took a course in undergraduate when I was an undergrad called numerical analysis, and it's a math course. And what we had an end of the semester project, and our project was to take 3 of the most widely used computer programs by engineers. It could be by whoever, just for science purposes, and put a problem into that computer system that you can prove the theoretical result is true with hard, rigorous mathematics, but create an incorrect answer from the computer. So what we had to do is we had to go into the code of the way whoever programmed it, go into the code, and we had to find weaknesses in the code and exploit the weaknesses. So we say, okay, look, in this line, they're not taking into account that what if you have a very large number here? It's doing something there, it's rounding too much, or so we had to exploit that. And so that was the end of your project. I used Mathematica, which is Wolfram. Wolfram is the one who makes, Wolfram makes a product called Mathematica, which is what I use with all my notes and everything. And so I did it on that one in MATLAB and something else. And it was fun. But that was the whole, you have to keep doing the theory because you can't get everyone too far away from it. It's just finding that nice balance. It's something that this generation and future generations are going to have to deal with, right? So, you would hate to be like the head of your engineering firm, right, and go build a bridge and it falls, and then you're like trying to justify it in court, and you're like, well, we just plugged it into this program, and it took the answer and trusted it. That's not going to hold up in court, right? Especially when people die. But on the other hand, it's so freaking good now, right? The algorithms that they have are so good, it's hard to bring these things down, right? So, anyway, well, all right, we'll get back to work. Next one is a repeated integration by parts. Repeated. What's the variable in this problem? T. What's that thing in front of T inside that cosine? Beta. It's a Greek letter. It's just a constant. We don't know what it is, but it's a constant, okay? So it may as well be 4T there, or 10T. So now I'm starting to think integration by parts, right? I've ruled out all the other possibilities. I need to choose a U. What's a good candidate for my U? T squared. Because in the new integral, right, it's going to not be T squared, it's going to be what? 2T, or let's just say T, because the 2 can always come out. So the power is going to come down, right? But I'll still have a T there. What's going to be the other thing in that integral? What type of thing is going to be there with that T in the new integral? Yes, but from the integration by parts, don't we have to, if we choose our T squared to be our U, then the dv here is the cosine beta t dt. So the antiderivative of that in the new integral is going to be what? Sine. So now in my new integral, I'm going to have a t in there, right? And I'm going to have a sine. So I got to do integration by parts again on that new one, which is why I'm calling this repeated integration by parts. See, the first integration by parts is going to reduce the power t squared down to t. Then I'm going to do it again to reduce the power t down to 1. So hopefully you kind of follow that. I'm trying to think through this before I do it. I'm not just sitting here going, integration by parts, set up the table, I mean, it's not robotic. There's thought behind this, all right? Okay. So my U, my du, my dv, and my v. What two parts go in this table from this integral? What two pieces? U and dv, right? I'm always going to grab those two. All right, the u that you said you wanted me to use was t squared. The derivative of that is 2t dt. Okay, the dv is everything else that was there that you didn't choose. So cosine beta t dt. Now you need to go from dv up to v. So you need an antiderivative. One over beta sine beta t. That 1 over beta comes from the fact that I have to do a little substitution there. When I do that, I have to scale it. So if you are having trouble going from that dv up to the v, you just need to practice on the side, do your own scratch work on your own time, because that's 5.5 stuff now, all right? It's a basic substitution. Yeah, unfortunately, classes like this, I mean, truly, when you walk in the next class, you're supposed to be pretty comfortable with the previous class lecture. Not like, oh, well, I partied all weekend, right? Super Bowl party started on Wednesday after class, and I've been partying since then, right? All right, let's rewrite this integral. This integral becomes ultraviolet. So how should you write that? I like to always put the constants first. So 1 over beta t squared sine beta t. Anybody else curl their t's at the bottom? Yeah. If you're going to write a lot of math, you can keep it from mixing it up with your pluses. Yeah. Yeah. Well, the one I have never been able to get around is my 5s. 5s and s's. My 5s and s's look too much the same. And do what? I remember that from Cal 1. Now, that'll last you until you have more than one variable. Okay, minus ultraviolet minus voodoo, but in an integral, right? So when I'm looking at voodoo here, whatever constants I'm going to pull out. So I have a 1 over beta, and I have a 2, right? So how about I just put a 2 over beta on the outside? Then my integral, and then I have what? T sine beta t dt. All right, let's vote. Are we good up to this? All right, so now I repeat the process. Why am I repeating the process? Because I don't know what the antiderivative of t sine beta t is. I don't know. So I need to do an integration by parts on this integral right here. So I will focus all my attention right now on just this integral. I want to go figure out what that is, and I'm going to do it down here. I'm going to do integral t sine beta t dt. I set up a new integration by parts. Now, you can use u and v again as long as you keep track of everything, okay? Don't get it confused with your u and v from before. So what u are we going to use here? T. Du is dt, right? dv will be our sine beta t dt. Really run out of room there. And that means our v is going to be what? Negative 1 over beta cosine beta t. So please help me rewrite just this red integral. What's it going to become? Ultraviolet, right? So negative 1 over beta t. Yes? Ultraviolet. Cosine beta t. So I'm doing my ultraviolet straight across here. Minus integral of voodoo. So I'm going to be doing this right here, these two multiplied. So it's going to be plus, right? Because this one of these is minus already. And the 1 over beta is a constant. I'm going to pull that out. So it's going to be plus 1 over beta integral cosine beta t dt. Any questions? You don't have to vote. Any questions? What's the antiderivative of cosine beta t? Because that's the only thing left in that integral. 1 over beta sine beta t. So I'm rewriting all of this still. Now here's my antiderivative. So I just bring my 1 over beta, right? Antiderivative of this is this. That's just the red part, right? That's just this right here. So what I need to do is I need to rewrite this right here. Everything in this bracket gets replaced with everything here. And this negative 2 over beta gets distributed, doesn't it? Okay. That's right. Sorry, I'm trying to squeeze this all in here so that I don't have to do it on a different page. I would hope on your work it would be a little neater. I forgot to close my bracket. So that's the red piece replaced. I did put the 1 over beta times 1 over beta, made it 1 over beta squared. And then now distribute that negative 2 over beta, and we should be at our final answer, which I'm going to write down here. We have 1 over beta t squared sine beta t plus 2 over beta squared t cosine beta t minus 2 over beta cubed sine beta t plus a constant. Repeated integration by parts. Imagine if that had started out as t cubed in the very beginning instead of t squared. You'd have to do it 3 times, right? Yes. Yes. That's going to be what we call a reduction formula. And that is going to be something like this. I'll show you, but not yet. Okay, we're not going to have time today for it. Okay. Yeah, because you would have to kind of justify your, I mean, I see you're seeing a pattern here, right? But what do you think your next one would be? I mean, if this was cubed, is that what you're saying? If this was cubed, are you saying that there would be another one out here? That's kind of dangerous. Yes? Over here? Yes, here? No, because it's in the formula, it's ultraviolet minus voodoo. It's over here, doesn't turn into negative sign. You're taking the antiderivative, not derivative. Okay, we have about 6 minutes. Let me just bring something up here. There's something that happens in functions that's happened a few times here that I'm hoping I can point out. Let's say we all know that, like, if I have a function, I take the antiderivative, we call it capital F of x, right? So if you have a function, little f of x, and you take the antiderivative of it with respect to x, you get the capital F of x plus c. Yes? Okay, so look at this. If you have a function, and inside of it, you have a linear expression, the antiderivative of this should be always capital F of x with that linear function plugged in plus c. But what happens if I were to take the derivative of this over here? You do the derivative of capital F, which is what? Little f? But then you eventually, with chain rule, have to take derivative of what's inside. What's the derivative of what's inside? A, right? Just A. So what you have to do when you go backwards is you always have to come in with the 1 over A here in order to kill the A that's going to come out in here. So this is a general formula that can be used for any function. So when we were back here and we were doing antiderivative of cosine beta x dx, our little f is cosine. Inside is a linear function, isn't it? Beta x is like ax. It's like 4x, like 10x. When I take the antiderivative of this, I know that I'm going to have to kill off the beta that's going to come out with chain rule. So I always just put 1 over beta. And then it's just what's the antiderivative of cosine? Sine beta x. Make sense? Plus c. Here's another one. The antiderivative of e to the 4x plus 1 dx. Well, e to the 4x plus 1, I know that my little f here is e. What's inside of it is linear, yes? So I know the antiderivative of this, I'm going to have to kill off the what? The 4 that'll come out of this, and then e to the 4x plus 1, because the antiderivative of e to something is itself. Another example of this would be, what's little f here? The secant squared thing, right? Is what's inside of it linear? Yes. What's a? Negative 1. So you would have to kill it off with what? A 1 over negative 1, which is just negative 1. What's the antiderivative of secant? Tangent. Secant squared, sorry. Just tan. Tangent of what was there. This only works if what's inside is linear. If it's not linear, this doesn't work. All right? One more. I'll try and help you. The function here is like 1 over something, right? 1 over u. What's the antiderivative of 1 over u? Natural log. But what's inside of it is linear. So you would have to come in here and kill off what? The pi. So you have to put 1 over pi. You said the antiderivative of 1 over something was natural log of it, right? But it's what in here? Pi x minus 1 plus c. The sooner you can like see this stuff, the quicker some of these things are going to go. These aren't things I'm telling you, go memorize this, memorize this. I would try and memorize something more like this. It's more abstract. It can be applied at any time. Okay, are there any questions? The homework assignment for this section is here. And I want to point out something to you. I'll put it on the board. That when you're doing your homework, if you're asked to find the antiderivative or something, and they have numbers like 2 and 4 here, and then they give you some function like, I don't know, x sine x dx, I want you to ignore the numbers, act like they're not there. All right? That's what I say here when I say treat the definite integrals as indefinite. When you have numbers here, these are called definite integrals. When you don't, they're called indefinite. We have not talked about definite yet. So any problems that have these numbers in your book, if you check your answer, it's not going to match your answer because they're different. It's more important that you just find the antiderivative, all right? That's what we're working on here. You won't be able to do all these problems because we haven't covered all the different approaches to integration by parts. But you should be able to do the first few, all right? Next class, we're going to do more integration by parts, and we'll start trig integrals. That'll be the same homework for next class. So that's the final assignment for 6.2. 6.2. That should be 6.1, shouldn't it? That should be 6.1. I don't know why I put 6.2 there. The page number's right. Have a great day, everyone. If anyone wants their quiz back, I have your quizzes up here. Yeah, let me stop this.